Good afternoon, and thank you to the University of Moratuva for hosting this session. It's a privilege to be here at a moment when Sri Lanka is facing profound climatic changes. Over the next hour, I'll explore how structural engineering is changing globally through sustainability, resilience, and digital transformation, and how these ideas can strengthen Sri Lanka's own infrastructure future. This topic is especially timely given the devastation from this week's storm, where many structures, drainage systems, and lifelines were overwhelmed. My goal today is to connect global engineering standards such as ASCE, COS 73, with real conditions Sri Lanka is facing, and to inspire you, students, faculty, and emerging engineers to take a leadership role in shaping a resilient future. Why this conversation matters. We're living in a world where climatic pressures are accelerating faster than our designs anticipated. What Sri Lanka witnessed in the past few days illustrates this perfectly. Rainfall intensities far above historical baselines, destructive winds, widespread flooding, landslides, and a level of infrastructure disruption that is both heartbreaking and instructive. Globally, we see that infrastructure is aging faster because environmental loads are increasing. Traditional design assumptions no longer hold. That is why many countries, including the United States, through ASCE, are shifting towards performance-based practices. Instead of designing only for compliance, we see how we design for outcomes, durability, carbon reduction, and resilience. This shift is not optimal anymore. Sri Lanka's storm has shown us how critical it is to think beyond code minimums and embrace future-focused engineering. Structural engineering today extends far beyond strength and serviceability. We now shoulder responsibility for sustainability, reducing embodied carbon, prolonging lifespans, selecting materials wisely, and resilience, meaning our designs must withstand and recover from extreme events. Sri Lanka's recent hurricane-level storm shows us how important paths, anchorage, foundation robustness, and redundancy truly are. At the same time, digital integration is becoming unavoidable. Sensors, real-time monitoring, machine learning-based demand prediction, and digital twins are transforming how we manage structural performance. As emerging engineers of Sri Lanka, you will navigate these overlapping domains, and your ability to integrate them will define Sri Lanka's infrastructure future. So, from prescriptive to performance-based design, for decades, most countries relied heavily on prescriptive codes, fixed formulas, minimum reinforcement, allowable stresses, right? But climate variability, urban complexity, and longer operational expectations are making prescriptive rules inefficient or insufficient, I should say. Performance-based design is growing globally because it allows engineers to tailor solutions to anticipate hazards, user needs, and long-term outcomes. Owners increasingly want measurable metrics, reduce maintenance cost, reduce carbon, better service continuity, and shorter recovery times after disasters. ASCE COS 73 is part of this shift. It asks us to define sustainability and resilience goals at the beginning of a project, and then to prove through documentation and analysis that design meets these goals. Sri Lanka's ongoing recovery absolutely aligns with this approach. The built environment is under intensifying pressure from all sides. Climate hazards, cyclones, extreme rainfall, coastal flooding, heat waves are increasing in frequency and magnitude. In Sri Lanka, the combination of dense urban development, floodplain encroachment, and steep terrain amplifies failures, right? The recent storm exposed how secondary effects such as drainage blockage, soil saturation, and cascading slope failures can multiply rapidly. Meanwhile, society expects longer facility lifespans, yet structures worldwide are degrading faster due to environmental stressors. This mismatch forces structural engineers to rethink durability, maintenance planning, and material selection. The solutions must extend beyond strengthening structures. They must include systems thinking across drainage, land use, social vulnerability, and climate projections. Whoops, I'm trying to, there we go. So here's today's session. First, I'll discuss sustainability in structural engineering, what it actually means for material systems and design decisions. Then we'll look at resilience strategies and how to design for hazard uncertainty. Then we'll explore ASCE COS 73, the new global sustainability and resilience standard influencing procurement and design practices worldwide. Finally, we'll connect these concepts to Sri Lanka's recent storm impacts and how digital tools can support climate adaptation. Each of these sections is linked, and together they form a framework for the next generation of structural engineering. Whoops, having trouble moving the slides. There we go. All right, so here's a little bit about my background so you understand the perspective that I'm bringing. I guess we all have our own perspectives and our own exposures and experiences. So I have been practicing for 35 years, and I've had the privilege of working across many continents. I would say five continents on performance-driven projects, from earthquake systems to offshore structures, adaptive reuse, and complex glass systems, load-bearing glass, like the TKTS booth in Times Square, New York. When I founded ISSE, my hope was to integrate sustainability and resilience more deeply into the engineering practice. What I've learned is that engineering success today isn't about following old templates, but it's really about adapting to emerging hazards, embracing digital tools, and making decisions that protect future generations. So that's the mindset that I'm hoping to talk to and encourage today. This is hard switching. Here we go. So here are a few sampling of projects that shape my thinking. I mentioned the TKTS booth. It really pushed boundaries by using glass as a load-bearing structural material. So it may have been the first structure ever that used only load-bearing glass as its primary structural system. And I also worked on a retrofit, also in New York. That's worth mentioning. It's 15 Union Square West, and it required a lot of integration between facade engineering, historic systems, and re-engaging the original iron frame structure. So, before the Industrial Revolution, so before the advent of steel, so re-engaging the original iron frame structure of the former Tiffany's building and adapting it for contemporary mixed use. I've also had exposure to New York City bridges, a very large suspension bridge in Lisbon, Portugal, called the Tagus Bridge, and a series of fixed offshore steel structures, large, enormous systems whose total heights approached the size of our Empire State Building in New York, with most of the structural mass extending below the waterline. So designing and evaluating structures of that scale reinforced how essential redundancy, ductility, and long-term monitoring are in high-hazard environments. So these lessons, especially around robustness and resilience, apply directly to Sri Lanka, where infrastructure must increasingly withstand extreme climatic variability while continuing to serve communities safely. Um, Right. So this is an environmental and a project that revolved around environmental systems. It's called the Staten Island Blue Belt. Incidentally, by the way, Staten Island, I believe, has the largest concentration of Sri Lankans in the United States, and that happens to be my home. So I have a lot of Sri Lankan friends. But and so this project is from Staten Island. It's called the Staten Island Blue Belt, and it's a example of sustainable infrastructure that manages stormwater using natural processes. So after the severe rains and the cyclone that you just experienced this week, we can see the value of nature-based systems, wetlands, retention landscapes, floodable zones that relieve pressure on drainage networks. When engineered and ecological systems work together, communities gain resilience. These projects taught me the importance of hydrology and geomorphology in engineering, knowledge that is extremely relevant for Sri Lanka as flood events intensify. So I've spent most of my career teaching as an adjunct, so part-time as I worked as a professional at several universities, including Columbia University in New York. I'm especially active in ASCE, the American Society of Civil Engineers, which actually has many international chapters as well. And my focus in recent years has been on sustainability as it relates to structural engineering, and particularly the Sustainability Technical Committee, which I lead and which also helps shape the development and the implementation of COS 73. Teaching has always mattered to me because the future of structural engineering depends on students, which I was one at some point as well, who can integrate mechanics, digital tools, and sustainability into a single way of thinking. I've also had the privilege of giving talks like this elsewhere, and I can say with confidence, based on what I've seen, that the University of Moratuwa stands among the strongest engineering communities in the region. Sri Lanka's future resilience, especially in the face of rapidly changing climatic conditions, will depend heavily on the talent that's being cultivated here. So what is ASCE COS 73? Um, it's ASCE's standard practice of sustainable infrastructure. This is the first performance-based sustainability standard that applies across the entire project lifecycle, from planning to decommissioning, right? It guides engineers and owners in measuring sustainability, resilience, life cycle cost, and environmental impacts, social performance. And what makes COS 73 so powerful is its flexibility. It is hazard agnostic and material agnostic, right? That means you can apply it in Sri Lanka for wind, earthquake, flood, coastal erosion, landslide susceptible zones, but you can apply it elsewhere in other geographic regions as well. More and more U.S. federal, state, and city agencies now are in the process of using COS 73 in their RFPs, in their procurement documents, drawings, specifications, which signals how rapidly the profession is changing. COS 73 matters because the world can no longer afford sustainability as a vague aspiration. We need measurable criteria. Climate and infrastructure pressures are converging. Extreme events like the devastating storm here in Sri Lanka, aging structures globally, and increasing demands for social equity and long-term value. COS 73 forces us to consider environmental impacts, stakeholder needs, and resilience performance jointly. For Sri Lanka, using COS 73 in reconstruction and future planning could be transformative. It ensures decisions are intentional and evidence-based and not reactive. Okay. So COS 73 is structured around three major items: management and planning, environmental and social performance, and resilience and life cycle performance. This is important. Many engineering failures, including what we witnessed this week, happen because planning and management decisions were uh, weak long before any structural analysis was done, right? So COS 73 integrates planning, environmental stewardship, community impacts, and resilience into one unified framework. It asks, did the owner define sustainability goals? Has the team evaluated environmental impacts? Does the structure meet resilience performance targets? And is the documentation traceable? This sort of approach, this structured approach, is exactly what nations facing climate volatility need. Okay. The SMP Sustainability Management Plan is one of COS 73's most actionable components. It requires owners, not just engineers, to define sustainability goals early. These goals might include embodied carbon thresholds, water reuse, long-term sustainability, or resilience against recurring floods. The SMP then becomes a tracking tool throughout the project. This is powerful for Sri Lanka. Imagine if major public projects defined sustainability and resilience goals up front and required engineering teams to document compliance throughout design and construction. What a difference that could make. So, LCCA, Life Cycle Cost Analysis. It's mandatory under COS 73. Too many infrastructure failures globally and here locally occur because short-term savings override long-term performance. LCCA evaluates total cost over time: maintenance, downtime, repair, hazard exposure, and replacement intervals. This is crucial after a recent storm. Rebuilding drainage networks, bridges, schools without LCCA may simply recreate those vulnerabilities. COS 73 encourages designs that minimize total cost over decades, not initial budget alone. And with AI and digital twins, LCCA is becoming more accurate and predictive. Resilience and hazard stressors. Resilience asks, can the system withstand, operate through, and recover from extreme events? Hazards include wind, flood, earthquake, heat, and the compounding effects we are seeing more often. Sri Lanka's recent storm is a real-world case. It overwhelmed drainage, destabilized slopes, damaged buildings, and disrupted transportation. Resilience requires redundancy, robustness, ductility, and anticipating future climate scenarios. not just using historical data. So COS 73 recognizes resilience as a design requirement, not an optional enhancement. Integrating into procurement and contracts. So in the US, we are seeing COS 73 incorporated directly into our RFPs, right? Requests for proposals and contract requirements. This means designers must document sustainability and resilience compliance at every stage. Sri Lanka could benefit greatly from this approach, especially for post-storm reconstruction. When performance requirements are embedded contractually, the whole industry shifts. Consultants, contractors, and owners all align on measurable outcomes. So COS 73 is adaptable to any country because it focuses on principles rather than prescriptive rules, right? It's hazard agnostic, meaning it applies whether risks are earthquakes, coastal, monsoon driven, or landslide prone. And it is especially useful for emerging economies that need clarity and structure as they plan for long-term growth. Sri Lanka's diverse climate zones, coastal, upland, and mountainous, make this flexibility increasingly and extremely valuable. So, embodied carbon in structural systems. Concrete and steel dominate global embodied carbon. As structural engineers, we often control 60 to 80% of a project's carbon footprint through system selection alone. Material choice becomes a carbon decision. One of the fastest ways to reduce emissions is through adaptive reuse. Preserve what already exists and reinforce it intelligently and extend its life. Sri Lanka, after the storm, will rebuild many structures, and embedding low carbon thinking now will pay enormous long-term dividends. Optimization is not about making structures lighter at the expense of safety. It's about choosing the right span, the right form, the right material, and the right load path. When geometry and analyses are used intelligently, especially with digital tools, we can improve performance while reducing carbon. Parametric design, automated load path analysis, and machine learning informed design exploration allow us to test hundreds of possibilities quickly, something earlier generations could not do. Adaptive reuse and retrofit are often where structural engineers can make the largest sustainability impact. When we preserve an existing frame and upgrade performance, we avoid the carbon and disruption with demolition and new construction. The structure becomes a kind of carbon bank that we are continuing to use. For designers, this means learning how to evaluate existing capacity, identifying bottlenecks, and introducing new load paths or stiffness only where needed. It may involve new diaphragms, supplemental bracing, local strengthening, rather than wholesale replacement. Some of the most satisfying projects I've worked on, I've already spoke of 15 Union Square West, involved carefully reusing historic systems, right, an iron frame before the Industrial Revolution, while meeting modern performance expectations. The lesson is that transformation without demolition is not just possible, it is often the smartest, most climate responsible choice. Okay. So long-term performance is where many otherwise well-designed structures fail. Corrosion, moisture ingress, fatigue, poor access for inspection can all shorten service life. For a coastal and monsoon climate like Sri Lanka, detailing is as important as member sizing. As structural engineers, we influence durability through cover, drainage paths, coating systems, joint details, and we influence maintainability by providing safe, logical routes for inspection and repair. COS 73 and similar frameworks asks us to think about performance over decades, not just on opening day. If you design with maintenance in mind, clear inspection points, replaceable components, realistic access, your structures will perform better and cost less over their lifetime. Durability is not an add-on, it's a core part of resilient and sustainable design. Systems thinking, right? So structure, envelope, site conditions. No discipline works alone anymore. Structure, envelope, and site hydrology all interact. The recent storm showed that even if a frame is strong, failures in drainage, cladding, or grading can still put occupants in risk. Systems thinking asks, questions like, how does water move across this site? How does the wind interact with roof and wall details? How does thermal movement affect structural joints? So by collaborating early with architects, mechanical engineers, and landscape designers, we can design details that work together instead of against each other. For example, roof drainage and overflow scuppers are both structural and civil issues. Retaining walls are both geotechnical and structural issues. When we embrace integrated design, we dramatically reduce the likelihood of surprise failures during extreme events. Okay, going back to my project examples. So these ideas that I mentioned are not theoretical. Right, so the TKTS booth in Times Square used innovative materials, glass as the main load-bearing structure to create an aesthetic yet efficient system. At 15 Union Square West, we combined adaptive reuse with new structural interventions, preserving the existing iron frame while adding contemporary residential and commercial functions, which included a double facade, incidentally, um, on the existing structure and also the 3 stories that were added to the top. The Staten Island Blue Belt, which I mentioned already, is another example where nature-based stormwater management works hand in hand with structural elements like culverts and retaining structures. Each project approached sustainability differently through materials reuse or landscape scale hydrology, but all relied on structural engineers, thinking beyond conventional boundaries. The message is that sustainable structural design can be bold and creative while still grounded in rigorous analysis. Okay, the low carbon roadmap for structural engineers. A practical, low carbon roadmap for structural engineers can be summarized in 3 words: reduce, reuse, optimize. Reduce means questioning spans and grids and unnecessary mass, sometimes adjusting the bay spacing or using a more efficient floor system, and that can yield major carbon savings. Reuse means prioritizing existing structures and components wherever feasible, strengthening and reconfiguring or partially replacing rather than starting from scratch. Optimize means using analysis and digital tools to refine geometry, select the right systems, and compare alternatives early when changes are still inexpensive. Designing for disassembly using bolted accessible connections and modular components can also dramatically reduce future demolition waste. If you start every project by asking, what is the lowest carbon structural solution that still meets performance, you will change outcomes in a very meaningful way. What is climate resilience? It's the ability to withstand, adapt to, and recover from climate-driven events. For structures, that means more than simply not collapsing. It means maintaining or quickly restoring function, limiting damage, and protecting occupants in critical operations. There's also a community dimension. A resilient hospital or bridge keeps the essential services operating when people need them the most. Importantly, climate resilience goes beyond minimum performance. Codes are often based on historical data. Resilience asks us to design for plausible future scenarios that may exceed those baselines. In a country like Sri Lanka, with cyclones, extreme rainfall, landslides, and heat, resilience must become a central design objective, not a special feature. To design resiliently, we must have a clear view of the hazard landscape, right? Here, the key categories include wind and cyclone effects, extreme rainfall and flooding, earthquake hazards, heat, and the compounding or cascading effects among them. For example, heavy rain may trigger slope failures, which then compromise foundations or lifelines. Local hazard mapping is essential. Global data sets are helpful, but only local studies reveal where riverbanks overtop, where soils liquefy, or where coastal surge concentrates. So COS 73 and similar frameworks ask you to identify relevant hazards explicitly, rather than assuming that one set of load combination covers everything. Once hazards are clearly understood, performance targets for each can be set in a rational way. Under extreme events, load path integrity is often the difference between damage and catastrophe. Robustness and redundancy ensure that if one element yields or fails, loads can redistribute without triggering disproportionate collapse. Ductility prevents brittle, sudden failures and buys time for excavation. For us, structural engineers, this translates into continuous load paths from roof to foundation, reliable diaphragm action, well-detailed connections, and attention to alternate load paths. In cyclonic winds or flood uplift, failures frequently start at the roof to wall or wall to foundation interface. Strong continuous connections may not be visually dramatic, but they are central to resilience. Thinking through what happens if this member is lost is a powerful design habit, right? Looking for that redundancy. So let's talk a little bit about my exposure to bridges and fixed offshore structures, and perhaps how that shaped how I think about resilience. Bridges and offshore platforms operate in extreme environments, continuous wave loading, strong winds, saltwater corrosion. Sometimes, depending where it is geographically, earthquake effects. Some offshore structures that I had been exposed to in the past had heights comparable to the Empire State Building, with most of that structure existing below the waterline. So you couldn't even really visually appreciate the height of that structure because you couldn't see it, um, because not that much protrudes above the waterline. So designing for these conditions require careful hydrodynamic analysis, fatigue checks, redundancy in framing, and continuous monitoring. When hazards are high, you can't rely on a single line of defense. You need multiple layers of robustness and an ongoing understanding of how the structure is aging. These same principles are increasingly relevant for coastal and riverine infrastructure in Sri Lanka. Uncertainty is now a defining feature of our design environment. Future rainfall, wind speeds, temperature extremes, and even usage patterns are harder to predict than in the past. Designing for uncertainty means using probabilistic checks, scenario analysis, and stress testing beyond minimum code requirements. We can ask, how does a structure behave if loads are 20 or 30% higher than design basis? What if two hazards interact? For example, flooding plus wave impact. Digital tools make it possible to run these scenarios efficiently. We may not design for every extreme, but exploring the response gives us insight into where we need additional robustness, redundancy, or protective measures. COS 73 turns resilience from a general aspiration into a set of explicit requirements. It calls for hazard identification, documenting which hazards are relevant to the project using the best available data, resilience performance targets, meaning defining how the asset should perform under different levels of event intensity, including functionality goals and acceptable damage states. Documentation and verification shows how the design, construction, and operation strategies meet those targets. So for Sri Lanka, adopting this mindset would mean that flood walls, bridges, public buildings are designed with a clear, traceable resilience objective. It also makes communication with stakeholders easy. Everyone understands what level of performance is being promised and why. Cyclone Ditwa is a sobering case study. Within hours, parts of Sri Lanka experienced severe flooding and destructive winds. Roofs were lost, retaining walls failed, and multiple districts suffered landslides. Transportation networks, schools, and essential services were disrupted, and thousands of families were displaced. This event is not an anomaly. It is part of a pattern of intensifying climate stress. For us as engineers, Cyclone Ditwa is both a tragedy and a data point. It reminds us that design storms based solely on the past may be inadequate. It also shows the importance of drainage planning, slope stabilization, robust roof anchorage, and continuity of critical facilities such as hospitals and emergency centers. So, a storm exposes specific vulnerabilities. Weak drainage networks and floodplain encroachment leads to water backing up in areas that should have remained dry. In some neighborhoods, roof uplift and wall failures indicated that connections and detailing were not adequate for actual wind pressures. In the hill regions, steep slopes, altered vegetation, and uncontrolled runoff contributed to landslides. You can correct me if I'm wrong later. Um, this is based on my readings and observations. And by the way, the landslides are not just geotechnical issues, they're structural and planning ones as well. By studying these failures carefully, Sri Lanka can prioritize retrofits, update local codes and guidelines, and adopt more stringent requirements where patterns of failure are clear. At a structural level, Cyclone Ditwa highlighted challenges such as foundation softening and scouring, especially near rivers and coastal zones. Uplift and lateral forces attack structures from multiple directions. In many cases, inadequate roof-to-wall anchorage allowed the wind to peel roofs away, exposing interiors and accelerating damage. We saw that some of the critical facilities were located in flood vulnerable areas or lacked adequate elevation and flood proofing. For future projects, these observations argue for elevation strategies, robust foundations, and stronger anchorage details, particularly for essential services. They also reinforce the value of proper site selection and land use planning, areas where structural engineers can and should have a voice. So this is where COS 73 can be particularly powerful for Sri Lanka. The standard encourages hazard-specific performance targets, life cycle thinking, and integration of resilience into procurement. For example, an RFP for a new hospital could explicitly require functionality after a 100-year flood plus wind speeds associated with a major cyclone, along with a life cycle cost analysis of different structural options. So it also encourages adaptive design, structures that can be evaluated, elevated, strengthened, or extended as conditions change. If Sri Lanka used COS 73 principles in its reconstruction programs, the company can move from repairing damage after every event to building an infrastructure portfolio that is progressively more robust and climate ready. Digital tools can greatly enhance climate adaptation. Sensors and structural health monitoring provide real-time data on how assets are performing. Digital twins of drainage networks and structures allows us to simulate intense storms and see where water or loads concentrate. Forecasting systems combine rainfall prediction with topography and soil data to give early warning of floods and landslides. For Sri Lanka, a coordinated digital strategy could include flood sensors in key basins, slope monitoring instruments in high-risk areas, and bridge sensors on critical routes. These are not science fiction ideas. Their technology is already being deployed in many countries. The opportunity here is to connect them into a coherent national resilience system. So there are opportunities for students and researchers at the University of Moratuwa. There's room for resilient design research. You may already be doing it, where new structural systems or retrofitting techniques are tested under simulated cyclone and flood conditions. There's scope for community retrofit programs, where students collaborate with local authorities to strengthen schools, clinics, or small bridges. There's also an exciting frontier in AI and data-driven engineering, developing models that predict deterioration, classify post-storm damage from drone imagery, or optimize retrofit strategies under budgetary constraints. Sri Lanka's recent experiences provide real-world data and motivation. Your research can translate that into solutions with global relevance. Let's see. So AI, what do I say? AI is really reshaping structural workflows. Parametric and regenerative design tools can quickly explore thousands of framing options, adjusting spans, depths, and materials while respecting code constraints. Automated code checking tools free engineers from repetitive tasks, allowing more time for judgment and creativity. AI does not replace human engineers. The best workflows, in my opinion, are human AI collaborations, where the engineer defines the problem, sets the constraints, interprets the results, and ensures that solutions are safe, constructible, and contextually appropriate. For Sri Lanka, AI-assisted workflows could help deliver more resilient, optimized designs quickly, especially important when reconstruction timelines are tight. SHM, structural health monitoring. uses sensors to capture real-time performance of structures. Accelerometers, strain gauges, displacement transducers, and corrosion probes can reveal how a bridge, building, or slope is behaving under normal and extreme loads. Early detection of deterioration allows targeted maintenance before small problems become major failures. For Sri Lanka, priority candidates for SHM include key highway and railway bridges, critical retaining structures, slopes above populated areas. Data from these systems can feed into risk dashboards, informing both engineering and emergency management decisions. When combined with AI, SHM can automatically flag abnormal behavior and help prioritize interventions. Digital twins. It's more than a 3D model. It's a live, data-connected representation of an asset or a system. For a bridge, a digital twin might integrate geometry, materials, sensor data, traffic loads, and environmental exposure. For a drainage basin, it could combine topography, rainfall, and flow data. With the digital twin, we can simulate scenarios, such as a 100-year storm, and visualize where stresses, deflections, or flood depths will be highest. After an event, we can compare monitored data with the model to identify potential damage. For Sri Lanka, digital twins of key corridors, coastal defenses, and urban drainage systems would be powerful tools for both planning and real-time response. IDEs, integrated data environments. IDEs pull information from many sources: design models, SHM sensors, inspection reports, climate data, into one single coherent platform. Instead of each discipline keeping separate spreadsheets and drawings, an IDE allows everyone to work from a shared source of information, of truth. This improves accuracy, reduces conflicts, and supports better decisions over the entire life cycle. For Sri Lanka, an IDE could link structural models, geotech data, and hydrologic models, helping engineers understand how changes in one domain affects others. It also sets the stage for advanced analytics and AI because the data is organized and accessible. The next generation of structural engineers will need 3 broad skill sets. First, mastery of mechanics and materials. This remains foundational. Digital fluency, comfort with modeling, data, and AI-assisted tools. And third, sustainability and resilience literacy. Understanding carbon, understanding LCCA, life cycle cost, hazard analysis, and community impact. Engineers who can operate at the intersection of these 3 domains will be in the highest demand. I highly advise engineers to stay curious, keep strengthening your fundamentals, and embrace new tools as they emerge, but always with a critical and ethical mindset. Some of the best projects I've worked on were successful because structural engineers collaborated deeply with architects, environmental scientists, coastal engineers, planners, and other disciplines. Climate challenges do not respect disciplinary boundaries. Flooding, for example, is simultaneously a hydrologic, geotechnical, social, and structural issue. At your university, you have the advantage of multiple strong departments in one campus. Work with peers in architecture, transportation, coastal, and environmental engineering. Take advantage of the fact that you're in proximity. The more comfortably you work across disciplines, the more effective you will be in delivering resilient, people-centered infrastructure. At its core, Engineering is an ethical profession. Our decisions affect lives, ecosystems, and public resources for generations. With climate stress increasing, our responsibility is expanding. We must consider not just whether a design meets today's code, but whether it is just, equitable, and robust enough for tomorrow's conditions. So this includes speaking up when we see unsafe practices, resisting pressures to cut corners, and advocating for solutions that protect vulnerable communities. The structures you design will stand long after today's political and economic debates have faded. The ethical choices you make now will shape the world your children and grandchildren will inherit. So, to summarize, sustainability is a structural issue. Our material choices, systems, and reuse strategies strongly influence carbon and resource use. Resilience requires forward thinking, hazard aware design that goes beyond minimum code compliance. And digital tools from AI to SHM and digital twins are transforming how we analyze, monitor, and manage infrastructure. For Sri Lanka, integrating COS 73 principles, climate aware design, and digital innovation offers a pathway to infrastructure that is safer, more durable, and more equitable. These are not separate themes, they reinforce one another and define the future of our profession. So, if I had a call to action, it's pretty simple. Be curious, be rigorous, be courageous. Use your time to build strong technical foundations while also exploring new tools and interdisciplinary perspectives. Push boundaries, but do so responsibly, with public welfare always at the center. Sri Lanka and the world need engineers who are willing to lead, to question old assumptions, and to design infrastructure that truly serves communities under changing climate conditions. You are truly in a unique position to shape that future. So there's a lot of potential for collaboration between your university and international partners. And I'm just going to try and name a few, including working with organizations on digital twins, resilience frameworks, and advanced structural systems. Joint research can focus on Sri Lanka specific challenges, cyclone resistant housing, resilient transportation corridors, nature-based coastal defenses, or AI tools trained on local data. You should welcome opportunities to explore such partnerships further, whether through student projects, faculty exchanges, or pilot demonstrations. We can develop solutions in Sri Lanka that have relevance far beyond its borders. So thank you for the opportunity to share these ideas with you today. It's really an honor to speak at the University of Moratuwa, especially at such a critical moment for Sri Lanka. If you want to continue the conversation, feel free to reach out to me by email or connect with me on LinkedIn or Facebook. My contact information is right here. I'm always happy to hear from students, researchers, practitioners who are passionate about sustainability, resilience, and digital innovation. Well, since this is a recording, if you have any questions or comments, you could send them to me by email or through social media. I'm particularly interested in hearing your observations from recent events in Sri Lanka, what you've seen in your own communities, and where you think research and practice should focus next. So, like I said, feel free to ask about COS 73, digital tools, specific structural strategies, or anything that really resonated with you. Okay. And I'll leave you with this thought. Engineering quietly shapes the world. Most people never notice the beams, foundations, drainage systems that you design, but they rely on them every single day. Your work will protect lives, enable opportunity, and help communities recover from adversity. So build boldly and wisely. If you combine technical excellence with empathy, ethics, and imagination, you will create infrastructure that not only stands, but truly serves. Thank you.